What's going on, everybody? Welcome to UW Marathon CS540 week 2 lecture on Uninformed search. So if you're new here, welcome. Be sure to check nearlyblog.com and visit this page. Then we come to the page I showed you just now. So in this week, we mainly talk about the uninformed search, and basically we talk 4 different kinds of search methods. One is BFS, which represents breadth first search. Second is depth first search. Third is uniform cost search. Fourth is iterative-deepening search. So let's take a look to all these kind of search methods and compare the complexity. So here I just use a PowerPoint that we use in our lecture to talk about all these methods. So first, let's talk about the BFS, breadth first search. So for breadth first search is actually a kind of uninformed search, and for what uninformed search means is, as you can see here, actually got some numbers which we call it the cost of the path. So for uninformed search, for example, if we go from S to A and from S to C, it's actually equivalent, since we assume that for uninformed search, the cost is actually a unit of 1. However, for informed search, there is actually a difference between S to A and S to C, since the cost from S to A is 1 and from S to C is 8. And we will pick the better one, which will be taught in the uniform cost search. So if there is no difference, we are going to have 2 things. One, of course, is the visited node. Probably just put in the left hand side. Visiting nodes. And second is the queue. So visited node is actually the thing that we're going to output after we finish our algorithm, while for queue is actually the thing that we're using our algorithm to find what's the next node, and we just append those nodes in our visited node, which is our output. So first, our S is the initial state in this graph, and G is the goal state. So what we want is we can go from initial state to the goal state with the optimum path. So first, of course, we can see our visited node is S and our queue is S as well. And for BFC, sorry, it's BFS here. So for BFS, it actually will append all the children for its parent to our queue. So that is, for S, we got A, B, and C. However, for visiting node, it will not append all of them at one stop. Instead, it will check one of them one by one. So first, we check A. Okay, A is not G, it's not our goal. Then we just go to the next. That is B. Okay, B is not G. Then C. So every time it will take actually the first node of the queue to find its children, and in this case it's S, and S got 3 children, that is A, B, and C. However, after we finish this loop, which is we find out A, B, and C, we just dequeue the first item, which is also the first in first out sequence. And after that, since we haven't found our goal, we are continuing our loop, and we are again using the first item in our queue as parents and to find its children. So here A actually got 3 children, that is D, E, and G. So we just append all of them in our queue, D, E, and G. However, we are not that eager to put all these things to our visited node at once. Instead, we are going to check them one by one. First is D, D is not G. Second is E, E is not G. Third is G. Okay, G is really our goal. Then we just stop here. So let's make a little bit changes. So for example, if we do have a G here, we just cancel all this stuff. We do have a G there. Then our Q for we will append G, D, and E. And so here we first go to G, find G, and G is our goal. Then we just stop here. But here I just make assumptions since normally we will put D, E, and G just in the alphabet sequence. So just now, let's take a look to this sequence D, E, and G. And let's take a look to the complexity of BFS. So complexity actually has two parts. One is the time complexity, second is the space complexity. So time complexity is how complex your algorithm that will take time to finish. And for space complexity is what you're doing, you're running your algorithm, and so what's the complexity of memory it takes from a computer. So as you can see for Q, let's assume like B is the branch for each node. So for example, if we have B equals to 3, then here A actually got 3, S got 3 children, A got 3 children, and B also got 3 children, C got 3 children, so on and so forth. And D is the depth of the goal. And in this case, if we have goal here, that is in our third level, and D here is actually equals to 2, since the initial state, the depth is just 0. And we also have M. M is the maximum depth of our graph. For example, if there were a lot of stuff downstairs, the M is pretty large. And as you can see, since BFS is to take the breadth in every level, so every level it actually got B of so for example, if this is the goal state, then we actually in this level, that is here, first is 0, 1, and second level, we actually got the B to the power 2. The number is B to the power 2 nodes, and here is B to the power 1, and here is B to the power 0. So as you can see, first level is on 1 node, second is 3 nodes, third is 9 nodes. So every time in our queue, we will actually append all the children from our parents. So we will just append all of them. And to just make it to the worst case, we put our goal to the very last node and in the very last sequence. So we are going to have, actually in this level, second level, we are going to have the goal is actually in the 9th node. So for the complexity, you actually put the goal in the very last of your queue, and the complexity of time is actually a big O of B to the power D. That is, you have to examine them one by one in your loop. And for the space complexity is actually similar, since you have to use B to the power D. You have to take all these nodes in your memory, and that is B to the D. Well, I know it might be a little bit, it takes a little bit more time and space complexity. So what if our algorithm or our computer do not have such much space? And this is why we introduce DFS. So for DFS, as you can tell from the name, unlike BFS, which is to take all the breadth to our queue first, we are going to deep as possible. So first of all, we'll still start from S. And unlike BFS, we'll append all the children of the parents, which is S, A, B, and C. We are going to just take one of them, or you could say the first one, that is A here. and just check. A is not the goal. So we put in the visit node, so we just continue our loop. And for A, we go to very left first. Oh, and by the way, DFS is also kind of uninformed search, so there's no difference between this path. And we assume all of them, the unit cost of all of them is actually unit 1. And next is D. And D is not go, so we continue our loop. However, D has no children, so here a different thing, unlike BFS. So for BFS, it's actually first in first out to cut your first item, which is kind of Q. But here is actually last in first out, that's kind of stuck. So we just kill D, and we back to our A again. And we are going to, for A, we still going to visit D first. However, D is already in our visit node, so we just don't visit D. Instead, we're going to visit E, and we append E here. So E is also in our visit node right now. However, E is not our goal, so we continue. But E has no children, so we just kill it, and back to A again. And the next one is actually G. So G is the goal, and we just stop here. So the visiting node for DFS is SAD and EG. So that is actually, you could say, somehow kind of simpler to BFC. So let's take a look to the complexity for time and space. As for time, if we assume the very worst case, here just assume that so here is probably another number, and G is actually in the very last sequence of the last layer. So what it does is actually it will go from S and check all of them, then back, then go to B, then check all of them and go to G. So for the time complexity, it might be the very worst case. That is because it will search G in the very last. And there is another even worse case. That is, if it's actually an infinite loop, it actually can never reach to G, that is here, since it will just continuously go down, which is common in our network, for example, the internet. So for DFS, there might be a possibility that you are unable to reach your goal, while for BFS, if we assume the G is in a finite layer, then we are able to visit the G. However, for DFS, if we assume that it is a infinite graph, then there is a possibility that you cannot reach your goal. And for time complexity, in our worst case, that's really worse. That is b to the power m. M is the maximum length, maximum layers in a graph. That is in this case in the very last. However, for the space complexity, it does have some changes, since every time you will just kill the previous one in order to get the last one. So also in our very worst case, that is from S all together down here. So in this case, it actually is M is the maximum length of your maximum layer of your goal, and B is actually how many nodes it has, and hence compared to BFS, the time complexity is actually worse, but the space complexity is better. So DFS might suitable for those computers who consume less complexity, but in this the time is not that important compared to the memory. So next, what I'm going to talk about is we're going to have kind of informed search, that is uniform cost search. And for informed search, now we are going to take all these kind of numbers, since it's really important they're not counted as unit of 1 anymore. So first we start from our S here, and we can actually calculate. So from S to A, it will actually cost 1. From S to B, it will cost 5, and from S to C, it will cost 8. And we just take the minimum one, so that is A here. And next we'll continue from A to D. We'll just accumulate them. So this is actually 4, and 1 plus 7, 8, 1 plus 9, that is 10. So now we'll compare this stuff with 5 and 8. And we can see 4 is the minimum. So we'll just go from A to D. However, D is not a go, so we'll just continue. And D has no children anymore. So we just compare 5, 8, 8, and 10. So the next smallest one is B, that is 5 here. And B actually got a children, that is from B to G, which is 4. So we just plus 5, plus 4 by 5, that is 9. That is another minimum value here. So actually you can see there are 2 different values. On G right now, one is 10 and another is 9. For 10 is from S to A to G, and 9 is S to B to G. But it really doesn't matter, we'll just take the minimum one. So now we compare, we already finished the 5 here, the B here. So we'll compare 8, 8, 10, and 9. So probably just start from C by sequence. However, C is also not our goal, and from C to G, which is plus 8 by 5, which is 13. So now we are going to compare these 4 digits. That is another 8. A is the minimum, so we just go to E. Actually, we don't have Q here anymore. So and E has no children. We just ignore that. And last but not least, for Gale state, it actually got 3 different kind of values, and we just take the minimum, that is 9. And finally, we come to Gale state. And the way that comes to Gale state is the minimum, which is from S to B to G, and that is 9. So for uniform cost search, you actually find the minimum, the optimum cost in order for you to go from initial state to Gale state. So next, I'm going to talk about a method that is in the middle of BFS and DFS, which is called the iterative-deepening search method. So let's take a look to the method. For iterative deepening search, it actually has a you could say assigned D. So at the very beginning, D is actually 0. So for IDS, it actually uses the DFS to search every time. However, it will confine its depth at every time. So for example, first is D, and our D is just S. If we have D equals to 1, then we just have the upper part, that is only A, S, A, and B, and C. So here we use DFS, so that is A, E, and C. And next we are going to have D equals to 2. And if D equals to 2, then we have this stuff. However, we are still going to use the DFS. That's from A, S to A, then A to D, then back, then to E, back to G, and bingo. So it's S, A, D, E, and G. And let's think about its complexity. One is time, the other is space. Since we assume that D every time, So for the time complexity, it's actually which is actually the same as BFS. And the reason is, if we still like this kind of stuff, and in the worst case our goal is just here, then this kind of method is actually has no difference between the BFS, even though you're using the DFS search method, since you still like need to examine all this kind of those since it's at the very last. So it's still big O of B, capital B. B is the breadth, and small d. D is the depth of the go. In this layer, there's actually b to the power d nodes here, and we need to examine all of them. So the time complexity is still has no difference between BFS. However, for space complexity, it's actually real different, since we are using the DFS method. So the space complexity is actually the same as d times b here. So as you can see, compared to time to BFS, the space is much smaller, and compared to DFS, the time consumes less. So this is actually a better way compared with BFS and DFS. So actually nowadays, not many people will use DFS in real world. BFS got some benefits, but most of the time we just use ideas, the iterative deepening search method. I think this is the end for all the contents in the second week. And next, I'm going to talk about how to write Python codes to realize all these kind of search methods. Okay, thank you very much, and see you in the next tutorial.